Hello students, in today's class we are going to study about the van der Waal forces. Before we start with the van der Waal forces, I want you to teach about weak bonds and strong bonds. Whenever we talk about any kinds of bonds in chemistry, they are classified as weak bonds and strong bonds. Here we are talking about all the kinds of bonds which are present in chemistry. Weak, strong. We've studied both the strong bonds. The first two are ionic bonds. The second were covalent bonds. The weak bonds, the first one is van der Waal forces. The second one is London dispersion forces. The third one can be hydrogen bonding, and so on. All the strong bonds are represented by a solid line. For example, over here I have an atom. Over here I have an atom. And both of them are bonded by a strong bond. But the weak bonds are represented by a dash of line. So for example, if I have one molecule over here and one molecule over here, both of them can be slightly or loosely connected by a weak bond, just to make sure that the composition is correct. So strong bonds and weak bonds. In weak bonds, in today's topic, we're going to study about the van der Waal forces in detail. And also I'll give you a short brief up about the London dispersion forces as well. And of course, hydrogen bonding, the bonding between the hydrogen atoms which are present in the different molecules. When they combine together, when they club together to form something which is a union. In molecular physics, van der Waal force, named after Dutch physicist Johannes Dirk van der Waal, is a distance-dependent interaction between atoms or molecules. It is distance-dependent. That means two molecules are distant from each other and both of them are dependent on each other, because even though they are at a huge distance, even though they are distant from each other, they will have some kind of connection. They will have some kind of bond, and this bond is a loose or a weak bond. Unlike ionic or covalent bonds, these attractions do not result from chemical electronic bond. They are comparatively weak and therefore more susceptible to disturbance. Always remember, as the name suggests, weak bonds are weaker than the strong bonds. Weak bonds can be broken easily. And if weak bonds are being broken easily, then there is no point in making them go through different kind of disturbances, different kind of conditions wherein they have to face the condition wherein there are chances of them breaking up. The van der Waals force quickly vanishes at longer distance between the interacting molecules. So I've shown two molecules over here, the molecule 1, the molecule 2. Correct? So this is the molecule 1, this is the molecule 2. And there is a van der Waal force between them. Now, if I make molecule 1 over here and molecule 2 over here, then there's a lot of distance between both the molecules. The distance has increased. So there are chances of this particular bond, the weak bond, breaking up. So the bond vanishes if the distance between the interacting molecules is higher. If the distance gets higher, the bond vanishes. Van der Waal force plays a fundamental role in fields as diverse as supramolecule chemistry, structural biology, polymer science, nanotechnology, surface tension, and condensed matter physics. Now, all of these are nothing but different kinds of technologies, different kinds of concepts which are very advanced. If I talk about the structural biology, now what do I mean by structural biology? That means, for example, let us take plasma or let us take blood. All of those are quite complex. It is not like one element, another element bonded together in one bond, and we have got our materials. The materials inside our body require both strong bonds and weak bonds. And that is the reason why wonderful forces are a part of many things. So, this is nothing but a part of structural biology. It also underlines many properties of organic compounds and molecular solids, including their solubility in polar and non-polar media. Now, what do we mean by polar media and non-polar media? Let us take two examples. Let's take the first example as benzene, another example as water. Both of them are liquid in nature, and that is the reason why we are considering both of them as solvents. That means you can actually dissolve something into it. But if you see the structure of benzene, it is carbon. Firstly, 6 carbons attached to each other in a cyclic ring. And then you have your alternating double bonds happening over here. Finally, hydrogen. Filling away the hydrogens. This is how benzene looks like. It is non-polar in nature. But when I talk about water, H2O, the O is in the middle, both the H is on both the sides. Since O is very electronegative, so if I consider this particular bond, the bond which is there over here, this hydrogen will get a little positive sign, this oxygen will get a little negative sign. Similarly, this hydrogen will get a little positive sign and this oxygen will get a little negative sign. So this thing over here becomes a pole, delta positive, delta negative. This thing over here becomes a pole, delta positive, delta negative. I can see two pole formations in one molecule of water. That is the reason why this becomes my polar solvent. Based on this and the solvents on van der Waals forces, we will actually understand what is going to get dissolved in the polar and the non-polar media. If no other force is present, the distance between atoms at which the force becomes repulsive rather than attractive as the atoms approach one another is known as van der Waals contact distance. This phenomena results from the mutual repulsion between the atoms' electron clouds. The van der Waals force has the same origin as Casimir effect, which arises from quantum interactions at 0-point field. Now, Casimir effect is a phenomena, is a topic which happens in quantum physics, but it is quite similar to the van der Waals forces. After all, physics, chemistry, biology are all part of nothing but science, and thus they would have certain similarities. Van der Waals forces include attraction and repulsion between atoms, molecules, and surfaces, as well as other intermolecular forces. They differ from covalent and ionic bonding in that they are caused by correlations in the fluctuation polarizations of nearby particles, a consequence of quantum dynamics. Despite being the weakest of the chemical forces, with strength of 0.4 to 4 kJ per mole, 4 to 40 MeV per bond, they may still support an integral structural load when multitudes of such interactions are present. That means if I do not have a single bond, but I have a group of bonds, I have a cluster of van der Waals forces, then those van der Waals forces unite together, come together, and they form a proper bond. The force results from transient shift in electron density. Specifically, the electron density may temporarily shift more greatly to one side of the nucleus. This generates a transient charge, which is nearby an atom, can either be attracted or repelled. When the interatomic distance of two atoms is greater than 0.6 nanometer, the force is not strong enough to be observed. In the same vein, when the interatomic distance is below 0.4 nanometers, the force becomes repulsive. So whenever we are talking about weak bonds, there is no giving away of electron. There is no accepting of electron. There is no sharing of electron. None of these are not there. Then what is exactly there? There is just two things. Some kind of attraction or some kind of repulsion. Just two things, attraction or repulsion. When we talk about attraction, it is again about the energy forces. When we talk about repulsion, again it is related to energy forces. So what decides whether it is an attraction or the diffraction or the repulsion? It is just the interatomic distance. When the interatomic distance is 0.4 nanometers or below, it becomes repulsive. When it is a good 0.6 nanometers, it is nice and attractive. The transition from van der Waals attraction to poly-repulsion to chemical bonding is discussed by Leonard Jones in 1933. Has been observed by atomic force microscopy in 2019 by Huber, Buena Policia, Maoski Albert, and Giesbel. Intermolecular forces have four major contributions. The first is the repulsive component. Now always remember the attractive component. That means when we are talking about the attractive force, not the repulsive force, we name it as van der Waals force. The repulsive one, we name it as Pauli's repulsion. This is the difference. So now Pauli's repulsion has another name known as Pauli's exclusion. Pauli's exclusion principle is quite a famous principle, but this is the basis of it. So the first contribution is a repulsive component resulting from the Pauli's exclusion principle that prevents the collapse of molecules. Attractive or repulsive electrostatic interaction between permanent charges in case of molecular ions, dipoles in case of molecules without inversion center. Dipoles means two poles, one positive, one negative. Quadrupoles, all molecules with symmetry lower than cubic, and in general between permanent multipoles. The electrostatic interaction is sometimes called the Keimson interaction or Keeson force after William Hendrik Keeson. He was the one who actually found out the differences between them. Induction, also known as polarization, which is the attractive interaction between a permanent multipole. What is a multipole? A pole with more positives and negative polars on one molecule with an induced multipole on another. This interaction is sometimes called as Debye force after Peter J. W. Debye. So if you can see, there are different forces. You have Pauli's repulsion or Pauli's exclusion. You have Keeson's force. You have Debye's force. But the main ones are the van der Waals, the London dispersion, and the hydrogen bonding. Dispersion, usually named London dispersion, interactions after Fritz London. Fritz London was the person who actually discovered the London dispersion phenomena, which is the attractive interaction between any pair of molecules, including non-polar atoms. arising from the interactions of instantaneous multipoles. Returning to nomenclature, different texts refer to different things using them as van der Waals forces. Some texts describe the van der Waals force as the totality of forces. That means they name everything under van der Waals. The attraction, the repulsion, everything, see, including repulsion. Others mean all the attractive forces and sometimes distinguish van der Waals, Hissem, van der Waals, Debye, and van der Waals, London. All intermolecular van der Waals forces are anisotropic except those between two noble gas atoms, which means they depend on the relative orientation of molecules. There are two kinds of things. One is isotropic. There are certain molecules which are isotropic in nature. Second is anisotropic. Anisotropic, that means they depend on the orientation, the new and the old orientation. Orientation of different kinds of molecules. When these molecules are oriented in a certain way, in such a way, and this orientation is actually anisotropic in nature. That means if you have two molecules and some other molecules over here, this position matters, and this is how it should go on. That is anisotropic in nature. The induction and dispersion interactions are always attractive, irrespective of orientation, but the electrostatic interaction changes sign upon rotation of the molecule. That is, the electrostatic force can be attractive or repulsive, depending on the mutual orientation of the molecules. When molecules are in the thermal motion, as they are in the gas and liquid phase, the electrostatic force is averaged out to a large extent because the molecules thermally rotate and thus probe both repulsive and attractive parts of the electrostatic force. Sometimes this effect is expressed by the statement, random thermal motion around room temperature can usually overcome or disrupt them, which refers to the electrostatic component of van der Waals force. Clearly, the thermal averaging effect is much less pronounced for the attractive induction and dispersion forces. The Lennard-Jones potential is often used as approximate model for the isotropic part of a total repulsion plus attraction. Now, what is the repulsion? The Pauli's repulsion. What is the attraction? Van der Waals attraction. Van der Waals force as a function of distance. Van der Waals forces are responsible for certain cases of pressure broadening, van der Waals broadening of spectral lines, and the formation of van der Waals molecules. The London van der Waals force are related to Casimir effect for dielectric media, the former being the microscopic description and the later will be the bulk property. The first detailed calculation of this were done in 1955 by E.M. Lifshitz. A more general theory of van der Waals forces has been developed. Now let's see the main characteristics of van der Waals forces. What are all the main characteristics? The first is they are weaker than normal covalent and ionic bonds. Of course, because they come under the category of weak bonds. Van der Waals forces are additive and cannot be saturated. You cannot simply saturate a van der Waals force. They have no directional characteristic. They do not change in directions. They do not have a characteristic which is directional. They are all short-ranged forces. That means they cannot go for a very long range. As I had told you in the previous slides, if molecule 1 and molecule 2, if I have two molecules, molecule 1 and molecule 2, if they distance out, there are very less chances of these forces to make up. They break off. They have no directional characteristic. They are short range. and hence only interactions between the nearest particles need to be considered instead of all the particles. That means if I have some molecule M3 over here, then we have to consider this particular thing, not this one. Van der Waals attraction is greater if the molecules are closer. Van der Waals forces are independent of temperature except for a dipole-dipole interaction. For dipole-dipole interaction, temperature can be used, but apart from that, they are independent. In lower molecular weight alcohols, the hydrogen bonding properties of their polar hydroxyl group dominate other weaker van der Waals interaction. In higher molecular weight alcohols, the properties of non-polar hydrocarbon chains dominate and determine their solubility. So it actually is a part of polar and non-polar. In the polar hydroxyl group, again we talk about the OH, and then we talk about the chains of the non-polar ones. Let us see a little bit of London dispersion forces as well. Again, London dispersion forces are shown as dashed lines, not as a solid line. And they work quite similar to the van der Waals forces, and both of them come under the weak bonds category. London dispersion forces, named after German-American physicist Fritz London, are weak intermolecular forces that arise from the interactive forces between instantaneous multipoles in molecules without permanent multipole moment. In and between organic molecules, the multitude of the contacts can lead to larger contribution of dispersive attraction, particularly in the presence of heteroatoms. Now, what do we mean by heteroatoms? Atoms which are different from each other are known as heteroatoms. London dispersion forces are also known as dispersion forces or London forces or instantaneous dipole-induced dipole forces. The strength of London dispersion forces is proportional to the polarizability of the molecule, which in turn depends on the total number of electrons and the area one covers in that particular spread. Hydrocarbons display small dispersive contribution. The presence of heteroatoms lead to increased LD forces as function of their polarizability. Example, a sequence can be, I can take R as any alkene. R is nothing but the chain of carbons. Always remember in organic chemistry, R is nothing but chain of carbons. That means if I say Ri, it can be a chain of carbon. It can be anything but an I attached to it. RBr, again chain of carbon, Br. RCl, can just be one carbon as well, CCl. RF, it can actually be a long chain of carbon and then an F. This entire thing can also be an R. This one carbon can also be an R. This is also R. This is also R. So here what do we have? Ri greater than Rbr, greater than RCl, greater than Rf. In absence of solvents, weakly polarizable hydrocarbons form due to dispersive force crystals. The sublimation heat is a measure of dispersive interaction. So with this, we understand what are van der Waals forces. We saw a little brief up about the London dispersion forces and eventually walked through what exactly are weak bonds. Thank you so much for watching this video. Thank you.